from Cleveland, and he'll be doing the presentation today. Once again, please feel free to ask, and we encourage questions. Thank you.
Yeah, thanks, Sherry, and hopefully everyone can hear me okay. Like Sherry mentioned, I'm the hose product manager at Swagelok in Cleveland.
Is now joining.
Yeah, like Sherry also said, please feel free to use the chat function at any time to ask questions. We'll stop occasionally during this webinar to answer questions, and then we'll also, of course, answer questions at the end. And for any unanswered questions, like Sherry said, we will be happy to set up additional time at your convenience to go through those questions to make sure they're answered properly. So again, email Sherry Ross with the email shown here, sherry.ross@swagelok.com, and she can help set that up with us, and we can get the right engineers and people on the phone to answer your questions. And again, I appreciate everyone joining our hose selection and troubleshooting webinar. I'm the hose product manager. I've been in the hose group for about 5 years in total. It was some a little bit earlier in my career. I've been at Swagelok for 25 years. And lately I've been the hose product manager now for the last 3 years. And it's been, a lot of fun, lot more to know about hose than people really realize. And that's part of what we do in this webinar. So our basic agenda today is we start relatively simple. We go through some background on hose types. Again, it seems pretty simple, but it can be a lot more complicated than you would think. And then what we do is we're going to go through the 2 most common hose issues that we've seen. We do some troubleshooting, a lot of troubleshooting with our field engineers and our various hose advisors around the world. And the most common things that we see are improper routing and static dissipation. And so we're going to talk a little bit about those. And then we want to talk about some common hose construction and how it can affect performance. And these are going to be related to permeation in soft core materials like PTFE. And then we're also going to talk about metal construction hose and how they fatigue in dynamic applications. And again, this will be about 40 minutes in total without questions. So feel free to ask questions again, and we'll stop along the way. So again, let's start off easy. Background on hose types. We want to go through different hose construction and how a hose is built. A hose is different than a tube. A lot of people think a hose is different than a tube and that it's flexible, but a lot of times tubing can be very flexible. A hose is actually different than a tube in that it's multi-layered. So the inner core of a hose is actually a tube. And in this case, in this picture, it's a Teflon or PTFE tube. That's the core material. There's different core material that see the actual media flowing through a hose. And that's pretty critical, of course, because it's what needs to be compatible with what the media is, whether it's gas or liquid, or sometimes solids. So the core material is very critical in selecting the right hose, but the actual core itself only withstands about 50 psi of pressure, which is, in the neighborhood of your garden hose, really, for that matter, much less than an airline that you would have in a shop air. So that core needs to be reinforced, and most of the time it's reinforced with a braid. It can be reinforced with other things, but most commonly it's a braid material, and the braid can be different materials depending on how strong it needs to be and how flexible it needs to be. So the braid in this case, there's a double braid. There's the black that you see in this picture is a fiber braid, and the gray is a stainless steel braid. Both can be used, one or other can be used depending on what the hose needs to do. And again, this needs to be considered when selecting the right hose for a job. The stronger the material, usually the less flexible the hose is. The weaker the material, the more flexible it is, but the lower the pressure rating will be. And then this braid can become worn on the outside. It can also be dangerous if it's damaged. The wires can puncture skin and cause problems. It's also very difficult to clean if you have a clean application. So the braid many times is covered, but this isn't required, but in this case, this picture is shown with a silicone cover, and these covers can act as different for different things. In this case, it's a silicone cover that's usually applied for the ease of cleaning the outside of a hose. There's different things that can be applied to protect a user from grabbing the hose and moving it around, or abrasion protection of the hose if it's being dragged along the ground. So different covers can be applied, and these need to be considered when selecting the right hose. And then, of course, every hose has end connections, and these end connections are attached in different ways. This particular one is very common. It's what we call a crimped end connection, where the hose barb is put into the Teflon core, and then a sleeve is crimped onto the outside of that end connection, which squeezes everything together. And it's important that this end connection is crimped on strong enough to withstand, of course, the pressure rating of the hose. This particular hose we're showing in this picture is a 1/4 inch hose rated at 3,000 psi. That end connection needs to have a 4-to-1 burst rating, so up to 12,000 psi, without separating from the hose, just from that squeeze. We always want the hose to actually burst.
Is now joining.
We always want the hose to actually burst and not the end connection. It's a safer failure mode, and so that end connection needs to withstand 12,000 psi in this particular case. So that was only one example. There's basically, in this case, 4 different types of hoses that we're going to talk about. The one we showed on the previous page was the second one on the line, fluoropolymer or PTFE or
is now
Teflon,
exiting.
or Teflon. The top one on this list is a metal hose. So this actual core of this hose is a metal tube that we take and we convolute it to give it flexibility. If you could imagine a very thin metal tube and you tried to bend it, it would kink very, very quickly. So the convolutions on that hose are needed in order to make it flexible. The end connection, of course, in this case is not crimped. We put a sleeve around it and an end connection on top, and we weld it all together. So it's a welded fit. It's very strong, and it withstands very high temperatures, very high pressures. We talked about the fluoropolymer one. And then a thermoplastic or nylon hose is used a lot of times because of its durability. It can withstand high pressure impulses, very soft materials in this, so it doesn't break. You can imagine harder materials like metal that would break very easily in high impulse impulse applications. If you imagine bending a paper clip back and forth, it will break very quickly. A thermoplastic hose, being made of all soft materials, will last much longer. And then lastly, a rubber hose, which is also very soft materials, nylon braids and things like that, so that it can withstand even more rugged environments. You can bend this and kink it and run it over with a tow truck, and in general it will withstand that kind of abuse very well, but it doesn't withstand the same amount of pressures. So when selecting the right hose for an application, it's always very important to take these things into consideration, because a very good hose could last a very short amount of time in the wrong application, and that's what this chart here is trying to show. Different hose materials are better for different applications, and so what we're saying here is a metal core hose is very good for high temperatures, it's very good for pressures, but it does not perform well in pressure impulse. Pressure spikes will break a metal hose very, very much quicker than a thermoplastic hose. At the same time, things like permeation, which we'll talk about a little bit later, a metal hose will not permeate at all, will not allow gas to permeate through the hose at all, where a thermoplastic or a rubber hose or a PTFE hose will. So different things play into how a hose will perform in an application. We've seen many times customers use a high-priced and high-quality hose in the wrong application, and it's simply the wrong hose for that job. and we can apply a different hose to that application and get far longer the life, 10 times, 20 times the life of a different hose, just because it's the right hose for the application. So this is, just intended to be basically a cheat sheet. All of our hose advisors, Swagelok Indiana, Cincinnati, have this material. If you have a hose that's causing you trouble, always start with looking at whether or not it's the right hose for the job, right hose construction for the job, because many times it won't be. Too many times we see a user of our hoses simply put in, reinstall the same hose for a continually failing hose, and it's just the wrong hose for the job. We're selecting a different type of hose usually does the trick. Some examples of that. This here is a picture of a tire press, and the tire press moves up and down 6 feet, 7 feet or so. It's quite a lot of dynamic motion. And the hoses you see that are curled up on the right side, insulated with some black material, they have a lot of dynamic motion as that tire press moves up and down, and they were failing within a month, in less than a month. They were just the wrong hose for the job. It was a rubber hose. It couldn't withstand the heat. It couldn't withstand the dynamic motion. And we worked with this user on selecting just a different hose type, and it was a more expensive hose, and so there was a little bit of pushback, of course, but at the end, this hose has now been installed for over 2 years and has not failed. So the slight increase in price in this case obviously has paid for itself, and the downtime is gone. The danger, the safety issues of having a burst hose these are steam lines, high temperature steam in an operator's environment is gone, and the whole plant is just running much smoother. And along those lines, we always say that a hose is very, very similar to a tire on a car. No one will go out and buy a car and expect the tires to be maintenance free and never need to be replaced or rotated, whatever it might be. A hose is very similar. A hose is the tire on a fluid system. It needs to have a preventative maintenance program. It needs to be planned to be replaced. They don't last forever, and they can be a very dangerous item because they're handled often, they're moved often, and they're usually a wear item that will eventually fail. It can be costly to have hoses go down because it's unplanned downtime. It can also be very dangerous. So every hose needs to have a preventative maintenance program associated with it. And I'm very shocked how rarely that's the case. It's very, very often that users of our hoses do not have any preventative maintenance program. They just wear them out until they fail and hope that it didn't cause any real damage. So I strongly encourage everyone to have a preventative maintenance program for hoses. These aren't just garden hoses, right? That wear out and you go out and buy a new garden hose and put it back in. They usually have something dangerous or high pressure or hot running through the hose, and it can be a big issue. And then lastly, hoses are the most commonly handled component in a fluid system. Every once in a while someone goes and turns a valve on and off. Fitting and tubing aren't really handled very often, but a hose is connected and disconnected very commonly in many applications. And because of that, they can be another safety issue with the handling of hoses. In this particular picture in the bottom, this person was using a hose for a steam application and didn't realize it had 200 degrees Celsius, 400 degrees Fahrenheit steam running through it, and went and rubbed against it and got what we call a steam tattoo. He basically burned his arm rubbing against the hose. And so always consider the different safety features with the hose. And for this reason, all hose companies really offer their hoses with a lot of accessories that you can apply to a hose to make it more safe to handle. Okay, with that, I think we'll stop if there's any questions so far. Just a quick 30-second break. Mike, I don't know if there's any questions in chat.
There is no questions on the chat. Off the top of my head, is there any recommendations for installation in the high temperature application?
Yeah, in general, the most common temperature we see is about 60 degrees Celsius, which I believe is about 130 degrees Fahrenheit, maybe 140, is safe to touch. So if you have a steam, which many times, all the time, steam is above that temperature, and a lot of media is above that temperature, we recommend to have insulation on the outside of a hose. We do offer insulation as standard, different companies do, but there's also different insulation material you can apply that you can find at local hardware stores, whatever it might be. But when it's above about 140 degrees Fahrenheit, we recommend insulation to be installed.
Okay. And we do have a question from the audience. What type of hose is typically used in a high vibration area? Example, around a pump.
Yeah, very good. So vibration, we would say, is very similar, has a very similar effect on hoses that pressure impulse does. It's a very similar effect. It's different reasons, but similar effect. So the best hose for a vibration application is a thermoplastic or nylon hose. The worst would be a metal hose. Now that can't always be applied, and that brings up a great example. If you have an application where you have vibration, but you can't have permeation, which is the flow of gas through a hose, which thermoplastic hoses will permeate. You have to have a trade-off, which one is better or worse, and that's why, again, hoses will eventually fail. But vibration is similar, again, to pressure impulse.
Okay. All right. Thank you.
All right. We'll move on now to 2 reasons that hoses generally fail. The first one being improper or basically understanding proper installation. And we see these all the time. Again, we have a group of field engineers, hose advisors that go out to the field and look at hose issues that come up. And these are just a small bit of examples of things that we've seen. Obviously damaged hoses. And it amazes me all the time how people will look at a hose and see it's been damaged and continue to use it, because it's scary, really. The one in the top middle, of course, has been kinked, and that's a very dangerous situation. And I think because we all have garden hoses at home and we kink our garden hoses and then unkink them, we don't think it's a big deal. An industrial hose that's been kinked is a really big deal, and we see that all the time as causing actual problems at customer sites. The one in the top right, of course, is not quite long enough. It's been pulled and stretched and kinked at the end connection. Again, the one in the bottom middle has been just run over and damaged. And these are hoses that clearly no longer function the way they should when they were first bought. And the classic is the kinking of a hose. And I think we all know what that is. We've done it again to our garden hose and don't really think it's a big deal, which for a garden hose it's not, but for industrial hose it is. And what kinking means is it's been bent tighter than its minimum bend radius. And what happens when kinking, when it bends tighter than its minimum bend radius, is the hose becomes oblong, like you see in the bottom right. And when that happens, the material is stretched beyond its elastic limit. So it now has permanent damage at the sides. And when that happens, as we know, the engineers out there would know, it does not bend back to its original form. Even if you try to massage it and make it look like it's oval or circle again, it's not as strong. It's been permanently damaged. It will not withstand the same pressure, and even more dangerously, it looks like it hasn't been kinked. So now you have a permanently damaged product in your fluid system that doesn't look like it's damaged. It looks like it's perfectly fine, and it just won't withstand the same pressure and will fail much faster. So we always make this a high priority, is make sure the hose is being routed in a way that will not cause this kinking effect. It will not permanently damage the hose. The most common reason for kinking a hose is right at the end connection. And you can see in this picture here, this hose has obviously been pulled down at its end connection, and that's going to eventually cause a failure point right there. It's not going to keep the crimp pressure, and the hose will pull out and have a massive failure, which could be very dangerous and could be very costly. So we always recommend planning for a 2 outside diameter length, so 2 OD length of straight length after the end connection before a bend starts. Now a hose is going to kind of bend where it's going to bend, and we understand that, but if you plan for that length, the hose will be stress-free at the end connection, and that's really what's important. We don't want to put stress on the crimp. We don't want to put stress on the metal material on the outside. We don't want it to cause any bending of the core tube and cause a kink and permanent deformation. There's also, obviously, hoses are put into dynamic applications. That's what they're used for instead of tubing most times. And because of this, we see a lot of failures in hoses because they've been bent the wrong way, and or they're not the right length to absorb the amount of dynamic movement like we saw in the tire press picture. For this reason, a group called NAHAD, which is a industry group for the design of hoses, developed a series of calculations, and the intent of this is not to teach these calculations, but it's to let everyone know that they exist. And our field engineers and our hose advisors are all trained on these to help determine the right length of a hose for a dynamic application. But we see very, very commonly a hose is selected. It might be the right hose for the application, but it's not the right length. And it's put into place and it looks like it is, and then the tire press moves, and the tire press moves farther than what was anticipated, and the hose bends or breaks because of the dynamic motion. So always make sure that you take these equations into account. And again, we can help with that. They're also posted on the NAHAD, NAHAD website. You can check those out and try to do them yourself. It's fine. They're not that complicated. And but the point is, make sure you take into account the full motion the hose will see when you select the right length. And sometimes it's a lot more than you would think. And then a very common thing that we actually see this in our manufacturing plants. I go around to our Swagelok manufacturing sites and try to correct this all the time. But a hose is installed, so the actual weight of the hose is doing damage on the hose itself, which you see on the pictures on the right and the left. The hose is installed so that the weight of the hose pulls down on the end connection, causing that same kinking motion at the end. This is done most often because a port or a connector is coming out horizontally and it's being installed on a different horizontal plane or vertically, and the installer doesn't want to have the cost of an elbow. And so because of the cost save of an elbow, this hose is being stressed and fails much faster than what would be expected. This type of force is even expounded when it's liquid. If this is a liquid flowing through here, the weight of the liquid will also pull down the hose, just making it fail much faster than you would expect. And the cost of an elbow is very, very minor compared to the constant replacement of this hose. And then lastly, and maybe most importantly, on dynamic applications, the moving a hose in what we call two planes or multiple planes is the absolute death of a hose. And what I mean by this is if you take the hose on the right, where it's coming out vertically from the floor or whatever, and it goes in horizontally in another plane, another application, another spot, and that is moving back and forth, you can't take that hose and put it flat on a table. It won't lay flat the way it's bent. That is putting a lot of twist on the end connections. It's putting a lot of torque into the core tube, and this hose will die extremely quickly. It's the fastest death that we've ever seen of any hoses. Putting in a different connection point, like you see on the left, with a static hose, or it could be tubing, that hose is now bending in what we call one plane. You can lay that hose flat on a table the way it is moving. This hose will last hundreds of times longer than the hose on the right. Torquing a hose in general is the fastest way to kill a hose than anything else. It will do it faster than overpressurization, over temperature, anything else. Torquing a hose is the worst thing you can do to a hose. And that's what you do when you bend a hose in multiple planes in a dynamic application. Okay, so the second most common failure mode we see is something called static dissipation. And this is maybe a little more complex, but what this is PTFE or Teflon core hoses. What we see is a pinhole leak that happens very commonly. We get this back all the time, and what these pictures are small spark points that happen through a Teflon core hose, and it causes a pinhole leak. So what is happening here is static charge builds up on the inside of a Teflon core hose, and the static charge, as it builds up from the media flowing through it, has to go somewhere. It has to go somewhere to a conductive source, and the closest conductive source, because Teflon won't conduct electricity, is the actual metal braid on the outside. When that happens, it's very similar to shuffling your feet across the carpet and reaching for the light switch. You get a shock. When that shock happens in a Teflon core hose, it has a lightning bolt shoot through the core, creating a hole, and that's now a leaky hose. Different media have more likelihood of this happening. So a lot of these are hydrocarbons, which are very common applications for hose. Also, steam is on this list. The list goes on larger than this, but these media have a very high likelihood of depositing electrons on the inner core of a Teflon hose. And as that deposit becomes higher, that charge has to go somewhere. Different things also affect this, like humidity, right? In the winter, when it's very low humidity and you shuffle your feet, you're going to have a high likelihood of shocking your finger on the light switch. Also, flow velocity inside a hose. If you shuffle your feet faster, it'll have a higher likelihood. Same type of thing going on inside of a hose. And so these things are very important to keep in mind. If you're selecting a Teflon hose, always keep in mind whether or not you're going to have likelihood of static dissipation problems. This is an example here you see on the left of a customer of ours that was using Teflon core hoses, and every yellow mark was a pinhole leak that they were detecting. And of course, our field engineers went in and were working with them. And what we decided was they needed to use Teflon due to various reasons, but they needed to also dissipate the static that was building up on the inside of the Teflon. The way we do this is by infusing the Teflon core with carbon. Carbon is conductive and will allow for a low amount of static discharge to happen inside of the core tube, so that this spark doesn't jump through to the metal braid. So on the picture on the right, what you see there is Teflon core hoses that have been infused with carbon, and it turns the core black. That's why the core is black. And that allows low amounts of static electron buildup to flow through the hose to the end connection without creating a spark. This completely solves that static buildup issue. Now, in some cases, we've had the question of, does this make the hose conductive? Is it considered a conduction wire, or a grounding wire for that matter, for the hose? And some users of hoses care about this, some don't. So if you don't, then bear with me for a minute, I suppose. But the answer is no. It doesn't make the hose a conductive wire or a grounding wire. The picture on the right, let's start with, is a metal core hose with a metal braid, metal end connections, full stainless steel, everything. And we applied a voltage across the hose and measured the resistance, measured the amps. And what we got was this hose had 0.4 ohms of resistance. This would be considered a grounding wire. This is a conductive hose. Very, very strong, very, very high current flow through this hose, full metal. The hose on the left is a nylon braided hose with a Teflon core with carbon infused into it. So it dissipates static buildup, but as you see here, it has 80 million ohms resistance. That's 200 million times higher than the metal hose you see on the right. It's not a grounding wire. It will not conduct enough electricity to be a conductive hose, but it will dissipate the static charge that builds up when you have different media flowing through it. If we did not have the carbon infused core, it would have basically infinite ohms. It would have infinite resistance. So what we do when we put the carbon infusion into the core is we reduce essentially the resistance from infinite to 80 million. So we make it at least dissipate the static buildup, but it is not conductive. So the important thing here is understand really what the need is of the hose electrically. And in some cases, it doesn't really matter. In some cases, one matters or the other. You can get static dissipative hoses that are conductive. You can get static dissipative hoses that aren't conductive, or vice versa. You can get any combination, but it's important if you have electrical issues to understand what the hose will do in that case. And when in doubt, with a PTFE hose, if you're using that, always get the carbon core. I always recommend getting the carbon core. It's nearly free. It's about a 1 or 2% add-on to the price, and it solves this problem all the time. So I always recommend that. It looks like it's a dirtier hose because it's black on the inside, but we've done testing and it does not have any leaching effect. It's not a coating, it's infused into the PTFE. Okay, Mike, I think with that, are there any questions at this point?
There is no questions right now on that.
Okay.
Is there any particular applications when you would use a conductive hose instead of a resistance hose?
There are. So there have been some cases where one piece of equipment is grounded, and it's important for another piece of equipment to also be grounded. And because of the way they're set up or the way they're placed, it's difficult to ground it. That hose actually acts as a grounding wire, and so it grounds the other piece of equipment.
Okay.
Now, there's also cases where it's important for two pieces of equipment that the hose is connected to be electrically isolated. So in other words, they're not conductive from one to the other. In those cases, of course, you want a non-conductive hose, and those are a little more rare than the first example. But in those cases, you want a non-conductive hose, but getting a static dissipative hose with the carbon core does not make them grounded to each other. They're still electrically isolated.
All right. Thank you.
Okay,
Hey, Doug, this is Al Caselli. How you doing?
good. How you doing?
Not bad. I got a question for you.
Sure thing.
With all that being said, what are the medias that you would suggest using the static dissipative hoses with?
The most common we see is steam, by far. Probably half of what we see being returned for static dissipative, or lack of static dissipation, I should say, electrical sparks, is because someone used a hose with a steam application that wasn't carbon core. The other ones on that list were a lot of the standard hydrocarbons, a lot of the lighter hydrocarbons, which Swagelok's involved with quite a bit. So most hydrocarbons show up on that list as being high problems with static dissipation. So that would be number 2.
Okay, thank you.
Sure thing. Okay, so moving on to understanding how different hoses are made and how they can affect performance. The first one we want to talk about is permeation, and we talked a little bit about it. Permeation is the flow of gas essentially through a solid material. And in this case, what we're going to talk about is flow of gas inside of a hose to the outside of the hose. Metal, essentially everything permeates. Even metal will permeate gas through metal. But it's at such a low rate that it's basically impossible to measure. It essentially, for anyone really worried about it, we're saying that metal doesn't permeate anything. But Teflon will permeate. And when you have a Teflon core hose that's 30 thousandths thick, 40 thousandths thick, whatever it might be, it will permeate gas through it. And it can become a concern. It can be a concern for 2 reasons. One is the gas that's permeating out of the hose can be expensive. It can be a calibration gas for an analyzer or whatever it might be. It can be expensive gas. It can also be dangerous gas. It can be toxic or explosive, or in a confined area, it can be an asphyxiation problem. So you need to make sure that you understand the permeation requirements of your hose. The smaller the molecule, like helium and hydrogen, of course, will permeate faster. Larger molecules permeate much slower. And the analogy I use, I think everyone probably understands it, but the analogy I use is permeation is like pouring spaghetti sauce on top of spaghetti. You can't see the plate underneath the spaghetti, but the spaghetti sauce will eventually reach the plate, right? That's permeation through a hose. We've done a lot of studying of this. This has been a high focus for us, and we understand a lot of these factors. The top 2 are pretty straightforward. The higher the surface area, the higher the pressure, the higher the permeation. And we know they're perfectly linear. So if you have a 2-foot hose versus a 1-foot hose, you essentially doubled the surface area. In that case, you're going to double the permeation rate. If you have a 2,000 PSI hose or you have a 1,000 PSI hose, you exactly double the permeation rate by doubling the pressure. Temperature also, as temperature goes up, molecules move faster, they permeate faster. But this is in relative to absolute temperature. And in Celsius anyways, 0 degrees Celsius is 273 degrees Kelvin. That's the absolute temperature. So moving up in temperature probably has a lower effect, just because on the absolute scale it's not as big. Relative to wall thickness, and this I'm talking about the PTFE core wall thickness. There's different hoses with different wall thicknesses, and as that gets larger, the permeation rate goes down by a square root function. But the last one on this list is the one we're really studying the most, and that's what we're calling sintering method. And what sintering means is essentially baking. What we're doing here is taking the PTFE core and we're baking it. And when you bake the PTFE core, it tightens the bonds. It pulls the PTFE, the Teflon, together and makes the holes between the molecules smaller and makes the permeation rate much smaller. And this is just a little picture of our permeation tester, but what we've done is a lot of evaluation of of different sintering methods and how they impact the permeation rates. And the reason we're doing this is because different sintering methods cost a different amount to do. We want to make sure we're doing the right thing, essentially. And if you take a non-sintered, non-baked hose, 1/4-inch hose, 3,000 psi, and we put it in this permeation tester, it permeates at about 150 cc's per foot of hose per hour. So in about 7 hours, you would permeate a liter. And in 56 hours, you'd permeate a gallon of gas. So it's a decent amount in just a 1 foot hose, 1 foot 1/4-inch hose. You would permeate a gallon in a little over 2 days. If you take that same hose and put it through what we call a slow sintering process. So it's a slow sintered hose now. And what a slow sintering process is if you imagine a pizza oven where you put a pizza in on one side at things like Donato's or whatever, and it slides through, it moves through a conveyor belt, and it comes out the other side of the oven baked. That's a slow sintered hose. It goes through a baking oven where it moves through, and it tightens the bonds. That same hose permeates now at 20 cc's per foot per hour. So it improves the permeation by 7.5 times. If we take that hose, the original non-sintered hose, and we put it in an oven like baking a cake, like we have in our houses, and just let it sit there for an hour, that's called a post-sintering process. And it tightens it even further. It's a more aggressive baking process. It now will only permeate 4 cc's per foot per hour. So we took the hose that was permeating at 150 and we dropped it by almost 40 times down to 4 cc's per foot per hour of hose. And so it really improves the performance. So the message here is understand if you have a PTFE core hose, which you probably do somewhere, and you're using it on gas, understand how important permeation is. These are those same numbers shown graphically. So the non-sintered hose in blue, you can see is permeating at 150 at 3,000 psi. And the post-sintered hose, again, it's a slower process, costs a little more to do. So it's not always the right answer, but in the case where permeation matters, it is a drastic improvement. It will not perform the same. Not all PTFE hoses are the same. And it's very important to understand how important permeation is when selecting a PTFE hose for a gas application. So again, summarize that, a post-sintered hose will maximize the performance, but be the most costly at the same time. A slow sintered hose will have a significant improvement and be kind of in the middle in cost. Understand, but when selecting between these, you need to understand how important is it? Is it just air running through the hose? It probably doesn't matter if air permeates, I would imagine. But in a lot of cases, it's critical to understand how much permeation is going to matter cost-wise or safety-wise. And it's always ask how that hose is made. Is it slow sintered, post sintered, or is it not even sintered, which would be the worst?
So, quick question: is
Yep.
that sintering, is that standard option? And if this is in the catalog, I apologize.
No, it's okay. We are actually going through and adding our sintering method to the catalog now. We did not have it in our catalog because people just didn't understand what it meant, to be quite honest. Now that we're doing a little more training on it, we are going to add that to our catalog. Swagelok's products, if you're interested, we have one product that's post-sintered, and that's our T series, BHTs and MBHTs and T series that we all consider one product. That's post-sintered. All of our other Teflon products are slow sintered. We have no products that are not sintered.
Okay.
But if looking at a different supplier, it's always important also to understand how theirs are made as well, of course.
All right, interesting. Thank you.
Okay. So our last topic for the day, before we hand it off for more questions, is understanding metal hose. This we brought up at the beginning. Metal hoses, of course, have a convoluted metal core. And the way these are made is we start with a flat strip about 0.008 of an inch thick on average, depending on the diameter. But really, that's only about 2 pieces of paper, so it's extraordinarily thin, and that gives it the flexibility. And this strip is welded, rolled, and then welded. And so it's basically what you have in the middle step there is a very long seam welded tube, about 0.008 thick. Obviously not flexible. It would kink very fast, break very fast. So it needs to go through what we call a corrugation process, and that puts the bends in it. You see on the right, and it makes it flexible now. It doesn't withstand much pressure, but at least now it's flexible. And this corrugation process, similar to the sintering process we just talked about, this corrugation process can greatly impact how the hose is going to perform. The most common, by far, almost without exception, is what we call mechanical forming, or roll forming is another term used for it, where rollers move around the outside of this thin tube, forcing, and the rollers are in the form of the convolutions. The rollers push themselves into the tube, forming the convolutions. And it's very fast to do. It's relatively easy, and what you get is the tube you see in the middle. And the first thing I want to point out with this is you can see the seam weld. It starts on the left side on the bottom, and it rotates around to the top. And I mentioned at the beginning, the fastest way to kill a hose is by torquing a hose. And what we're doing by making a mechanically formed metal hose is we're torquing a hose. Even before it's braided, even before it's installed, it is basically being killed, unfortunately. And what will happen is, as this hose is bent in a dynamic application back and forth, it will crack at the root, because where the root was formed by these rollers, it's been work hardened, it's been stretched, and it's been torqued, and it will eventually crack. It will crack actually relatively quickly. And things like vibration, what was mentioned earlier, things like dynamic motion, pressure impulses will cause these cracks. And this is almost the only way hoses are made, but a few suppliers make a hose that's referred to as hydroforming or crimp forming. And the way this is done is the inside of the hose is pressurized with water to thousands of PSI, which would burst the 0.008 inch thick tube, except it's inside of a mold, and that mold is in the shape of the convolutions. So it stretches to the point where it forms the, instead of bursting, it stretches to the point where it forms the convolutions. And the advantage with this is it doesn't have any work hardening, because everything is pressurized to the same amount, and it completely eliminates any twisting in the hose. It becomes much more flexible, much less work hardening, and eliminates completely the work hardening. The disadvantage is it's slower. It takes a lot longer to make a hose, and so therefore that comes out a little bit in the price. It takes a little more technology also to do it, more complicated machinery, and a little more know-how on how to make the hose. But the performance improvement is drastic. And what we've seen here in the bottom bullet there is, in dynamic applications, hydroformed hoses will last 10 times or more, we're actually learning now, than a mechanical rolled hose. So again, there is no one right answer, because hydroforming hoses come at a price, but they will last far longer. And similar to understanding the needs of permeation with a PTFE hose, it's always critical to understand the dynamic motion needs of a metal core hose. If a hose is not going to move at all in the application, then mechanically forming is probably okay. If a hose is going to be moved and handled and maybe see vibration, then mechanical formed hose will fail very, very quickly, and a hydroformed hose is always recommended. So again, always know how the hose is made when selecting a metal core hose as well. Okay, and I think with that, we're ready to hand it off with any questions, but as a quick summary, understand what hose type, first of all, is best. Make sure it's routed correctly. Make sure you understand static dissipation needs. And then for a PTFE hose, always know the permeation requirements. And for a metal core hose, always know the dynamic requirements and how those hoses are built.